Okay, I am going to be talking about how we are assessing residential use pesticides and their risks to wildlife and to drinking water in the pesticide program, and what particularly we're doing for assessment on turf. Overview, I am going to give kind of a brief overview of how we assess risks in general, but I'm going to focus, and I'm going to talk a little bit about terrestrial risk. I'm mostly going to focus on risks to water that's used by wildlife for habitat, and also water that's used for drinking water. I'm also going to talk some about how we do our simulation modeling and how we use monitoring data. And a little bit on risk assessment, putting it all together. So let's start with toxicity. That's the hazard assessment part of it. The words we use are survival, reproduction, and growth. That's, did it die directly from the pesticide, or did it impair its ability to reproduce, or did it impair its ability to grow? These are the first one you consider the acute endpoint. I use an LC50 and an LD50 to measure that. Reproduction and growth are usually what we get from chronic studies. And that's the duration part of it. We look at a variety of taxonomic groups. I talked about that in the previous study. Birds and fish and aquatic invertebrates. And we also look at the different kinds of environments that this could occur in. Terrestrial environment, or we could be talking about freshwater environment or marine environment. So when it all comes together, an endpoint that we might assess for toxicity would be something like chronic toxicity of freshwater invertebrates is 1.5 ppb based on a Daphnia magna study. So these are the kinds of things we end up using in our risk assessments. And for eco-risk, we'll have, depending upon the compound, between 8 and 15 of these that we do our risk assessments against. I have one slide on terrestrial assessment. We do the aquatics. There's a lot more interest in it, but we also assess the risks to terrestrial environments. And the key to that is something called the Kanega nomogram. It's based on two papers, one from the 70s and then an update to the same idea in the 90s that relates the concentration that occurs on foliage and certain classes of insects, small insects or large insects, to the application rate. And it's just a simple linear relation. And there are different classes of plant material. There's short grass and tall grass, and bushy plants and fruits and pods, things like that. So we have several different classes of plant materials that the pesticide could be on, and then we can estimate how much pesticide could be on that food item based on the application rate. In the last couple of years, we've expanded that very simple idea by taking into the fact that if you have multiple applications, the pesticide is going to degrade between applications. That was part of what Mark was talking about just previously. And the second thing is, we know that for unit weight, larger animals eat less food. Smaller animals eat more food per unit body weight. But they also metabolize things a little faster. High metabolism, the toxicity tends to be a little lower for small organisms than high organisms. And we've built those two, what they call allometric scaling factors, into the model. So we can account for changes in toxicity or risk from pesticide due to changes in body weight. So compared to what we were doing, say, in 2001, we've gained some sophistication there. For aquatics, the first thing is we do tiered assessments. We do something very simple and basic. We have two models. They produce a single value for different durations. So there'll be a peak value and then a 4-day mean and a 21-day mean. The 21-day mean is one for comparison to chronic endpoints, for example, they have one single hardwired scenario in it that represents a very highly vulnerable site. I do an assessment based on that single value from these models. And if I pass, I've done something very simple and cheap on my part to show that there's little risk from the pesticide. That saves us a lot of resources. The two models, GenEC and First GenEC, is for ecological risk, and First is for drinking and water. And why there are two different ones is because the scenario we've wired in is a little bit different. I'll talk about how they're different here in a couple of minutes. If you don't pass at Tier 1, you go to Tier 2. And we use two models at Tier 2 that are linked together, PRISM and exams. Stu talked some about PRISM before. PRISM is a model. It's called the pesticide root zone model, but we use it mostly for predicting the amount of runoff you can get. And it's really designed for agricultural fields, which is a bit of a problem, and the main one I need to address here. And then exams models the water body and the processes, the fate and transport processes that can occur in a water body. When we use PRISM and exams, we aren't getting a single value out of it. We put in 30 years of data, and you get applications made over 30 years, and you get all the rainfall events that occur for 30 years. And we monitor the pesticide concentration from all the runoff events that occur over that time into the water body and watch the concentration profile. And then we use that information to do our risk assessment. We do happen to pick a single value out of that. It's the 1 in 10 year peak. So if you took 30 years of data, found the maximum value in each year, and ranked them from greatest to least, go down 3 from the top, that would be the value that recurs every 30 years. It's kind of like a 1 in 10 year flood or a 1 in 50 year flood. It's the same kind of idea, and it's calculated in the same way. The key difference between Tier 1, which is this hardwired scenario, and Tier 2 is the scenario. And the scenario, in a lot of ways, is how we set the level of risk that we are concerned about. And that scenario varies from crop to crop. Scenarios have two parts. There's a static part that doesn't actually change from place to place. And that's the water body geometry and the watershed geometry. And those are things that are very hard to control for, and particularly for the eco-risk. We have a lot of trouble getting information how ponds vary from place to place across the country. So in lieu of trying to gather that data, which we haven't been able to do, we're using a standard watershed across all the country, which at least makes sure that everything's on an equal footing. The second part is the variable part, and that does vary from place to place. And we try to set that so that a site for a particular crop would represent a site that's about at the 90% vulnerability for that crop. You'll hear reasonable worst case or worst case, or we try to set them so they're a 90% site. They're not the most vulnerable site. We pull back from that somewhat, or we try to. We have two standard watershed geometries. One's called the standard pond. It's for eco-risk, and it's hardwired into GenEC. And the second is the index reservoir, and that one's hardwired into First. So that's why we have two different Tier 1 models. Our standard pond has a 10-hectare watershed, about the size of a single agricultural field, and it drains into a 1-hectare pond that's 2 meters deep with no outlet. It is a pond, but it is a surrogate for a bunch of water bodies that we would expect to be highly vulnerable and occur at the top of a watershed. And those things would be things like prairie potholes, playa lakes, small wetlands, and first-order streams. So it's a stand-in for all these kinds of water bodies.